Welcome back. Last time I tried to convince you that outliers and non-normal distributions can influence statistical results in unfortunate ways, even when the data is accurate and well measured. I gave the example of income, a known skewed distribution because of the astronomically high incomes of a few. And I showed how it biases both the mean and the standard error upward. What I didn't mention yet was how to fix it. There are two basic approaches to dealing with challenges caused by data, regardless of whether the root cause is error, poor measurement, or good quality data with outliers or non-normal distributions. There's actually one other approach that we're going to ignore for now, which is to simply get better data. That doesn't deal with the problems that we're mostly interested in right now, which is when it's good data. So the first of the two basic approaches is data transformation. That is, any kind of modification to the data before it's included in statistical tests. If the idea of intentionally messing with your data worries you, you're in good company. But there are some ways to transform data that are responsible and helpful, at least in certain circumstances. The second approach is to use what's called robust estimation techniques. Robust estimation encompasses a variety of modifications to statistical tools, not to data. These modifications can reduce or eliminate some of the problems that arise from data, violating some of our assumptions. Before we go on to talk in detail about these approaches, I want to pause for a second to talk about the word assumptions. Because in statistics, assumptions are specific, formally stated conditions required in order for a method to be correctly applied. They're sort of content validity for our methods. Some assumptions, though technically true, have been shown to have little effect on estimates and can frequently be ignored. One such example we've already talked about is the common treatment of multi-category ordinal scales, like, to what extent do you agree or disagree with the following statement? Treating those as interval instead of ordinal is one example. This violates the assumption that differences are comparable, that is, that 1 point is the same difference, whether it's between 1 and 2, 3 and 4, 6 and 7, and so on, but it opens up many more methods and typically produces very similar findings to methods specifically designed for ordinal variables. Violations of other assumptions can lead to results that understate, overstate, or even reverse the direction of relationships in the findings. Importantly, in the context of statistics, assumptions are not normative, and they're not causal, nor ideally are they hidden. They're not casual, so they're not just something you sort of don't recognize or realize are there. They are technically and clearly defined, and it's important to know them. Now, returning to the main topic, let's talk about data transformation first. Unless a data point is known for certain to be outright erroneous, such as if it exceeds the possible scale, adjusting or removing individual cases is problematic. But there are slightly less troublesome variants on this that treat all of the data meeting certain criteria in the same way, rather than picking one or two based on what you see. These include trimmed estimates, that is, removing a certain percentage of the highest and lowest values, Windsorizing, which is like trimming, but replacing those values with the most extreme untrimmed values, or a value with a specific z-score, rather than dropping them entirely, and M-estimates, which is trimming but optimized using an algorithm to determine the optimal percent to trim in order to produce robust estimates. Trimming can produce more stable estimates by reducing the potential for influential outliers. By stable estimates, what I mean is that if you were to take multiple samples, if you were to use a trimmed estimate, in certain circumstances, those trimmed estimates would be more consistent with each other because they tend to cluster around those central cases than the estimates that are more likely to have those influential outliers. But it can also cause other types of bias. In fact, its purpose is essentially to bias standard errors downward, which can give us false confidence in the strength of our findings by shortening the confidence intervals if we're not careful to adjust. That is, if you're automatically getting rid of or moving in the cases at the end, you're always getting to get a smaller standard error than you would have in the first place, which means a shorter confidence interval than the true data would have told you. Data transformation is less technically problematic, but it complicates the interpretation of results. Transformation works by performing the same operation of every value of a variable. It's often used to produce more normal distributions or to model nonlinear relationships. You've already encountered one kind of transformation in the form of z-standardization. Other common transformations include taking each value to a specific power, taking the root of it, taking the reciprocal, that is 1 over the values, the logs or natural logs, and reverse scoring. Unlike trimming, no data is discarded or ignored in a transformed variable, but this comes at a price. Variables that were previously in natural units, like age, income, sales volume, and so on, end up expressed in artificial units, so you end up with 2 standard deviations of age, or 3.5 square roots of income. These are much more difficult to interpret, and you have to be much more careful when you're using transformed variables, especially when you're transforming multiple variables that are being looked at together. Because of this, many transformations are more useful for abstract modeling, such as a health insurance company estimating how much more a smoker will cost than a non-smoker to treat on average. They're more useful for that often than for common sociological questions. In general, except for standardizing variables, it's best to avoid trimming and data transformation unless specific types of adjustments are normative in the subfield you're working in. So in some subfields, for example, income is regularly logged before being analyzed because it produces a more linear form. But if that's not the case, usually it's best to avoid that unless you're specifically told to, or unless you know that that's normal for the field you're in. By contrast, robust estimation techniques work by simulating a variety of samples. The most common way to do this is called bootstrapping, and consists of drawing a large number of samples, often 1,000 or more. Each sample is the same size as the original, but the samples consist of random values from the original sample taken with replacement, so that previously picking one value doesn't decrease the probability of it being picked again. So you have 1,000 values that are actually in the data, for example, but it's not the same mix of 1,000 values that you had in the original data. These samples then can be used to estimate a confidence interval based on the proportion of bootstrap estimates falling within a given range. But more commonly, what bootstrapping is used for is to estimate what's called a robust standard error. By building a sort of artificial sampling distribution, bootstrapping can give us a more stable estimate, and often more accurate estimate of the standard error than the simple standard error equation you already know. Bootstrapping nearly always requires a computer, though, because of the number of samples necessary. And there are other kinds of robust estimation. But robust estimation, regardless, does not bias the statistics or the standard error like trimming. It doesn't change the unit of the score like transformation. And it's often preferred when data are non-normal. In some cases, the best course of action may simply be, though, to leave things how they are and deal with the additional uncertainty or some potential bias. Regardless of what you choose, though, it's important to understand a range of adjustment techniques that you may see mentioned in articles or books so you can evaluate their appropriateness and potential downsides, and to understand some techniques that you might use and what assumptions and what effects you need to think about before you use those. Thanks for watching. See you soon.